Okay, so here's problem number 3. Let's talk about what's going on here. If the limit as we go to infinity and negative infinity is infinity and negative infinity, we know the end behavior has to go like this, which means that the numerator has to have a higher degree than the denominator by some odd number. So I really want something like an x squared over x function or something like that. And let's see, so I'm going to start sketching the graph as we go here. And hopefully we can work it out relatively simply, so I know it goes like this and like this. If the limit as x goes to -2 does not exist, that means we have an asymptote. How do I know it's an asymptote? Well, rational functions are nice things to talk about because for the most part they're well behaved. They only have discontinuities or breaks in the and breaks in the domain at holes or asymptotes. So I know there's an asymptote there. If it existed, then there could be a hole there. Let's see. This part here, if the limit as x goes to 4 is 5, 6, but f of 4 does not exist, that means there is definitely a hole over here somewhere at 4, 5, 6. And if we've got roots at -1 and -3, that means that there's, -1 and +3, those are the x-intercepts. And the fact that it doesn't exist at x equals -2 means that it's got to go up the asymptote on one side and down on the other. I don't think, well, let's see, what do we have here? Let's start with this. If x equals -1, we can do x plus 1 and x minus 3 in the numerator. We'll call it f of x. If there's an asymptote at x equals -2, then I know x plus 2 is in the denominator. And what else do I know? I know there's a hole at x equals 4, so I've got an x minus 4 in the numerator and an x minus 4 in the denominator. This does give me an x cubed in the function and x squared in the denominator, so that is going to work out to be having the right end behavior. So I think I'm done. This is it. So the graph is going to look something like this and something like this. We can check it out. What's the y-intercept? It's going to be 1 times -3 divided by 2 is -3/2. Yeah, that makes sense. The y-intercept there could be at 0, -3/2. So there's our function and our graph. As I said, we study rational functions because they're pretty well behaved. They do things we expect. They either have a hole or an asymptote. There's nothing funky about that. We can kind of tell where the ends of the graph are going just by comparing the degree of the numerator and denominator. Here's one to think about. If I were to graph y equals the square root of x plus 9 divided by the natural log of x squared minus 4, that is definitely not a rational function because the numerator and denominator are not polynomials. And even if you look at it on the calculator or on Desmos, it's not entirely clear what's happening here. It turns out there's an asymptote here, and there's an asymptote here, and there's a hole here, and it goes down the asymptote that way. There's a hole here, and it goes down the asymptote that way. And then this one comes down the asymptote and over to there, to that point. And this one comes down the asymptote, and eventually it goes like that, which is really hard to see on the calculator. So here's a problem for you to think about and work out. Why does it behave this way? Why are the holes there? Why is there nothing in the middle of this graph? And why does it go up at the ends? Why are there asymptotes? And where are the asymptotes? And where's that point there? I'll let you think about that. It's harder to do than a rational function. So we study rational functions because it lets us talk about limits. It lets us talk about holes. It lets us talk about continuity in a well-behaved system, as opposed to something like this last one that we can talk about the same things, but it's not a well-behaved kind of graph, and it takes a lot of thinking to get that done. But something to think about. Have a good time with it. Bye.